Test for sound. Okay, we're working. When I try to describe to my students about chemistry, sometimes I say it's like learning a new language. Right? You have to be able to speak chemistry in order to do stuff. Like if I talk about sodium thiocyanate, if you have no freaking clue what a sodium thiocyanate is, well then how can we do chemistry together? Right? But I mean, how is that different than when my daughter is learning how to read? Her vocabulary is pretty basic right now. She's in grade 1, right? She can do words that have like maybe 6 letters or less. Maybe she can do a compound word, like if it is like cowboy, maybe she can handle that, right? But like she's pretty basic. But you know what she's got down is her letters. She knows her ABCs. And that's what we've hopefully kind of covered so far is our periodic table, knowing things like all of the elements on the table. If I were to give you a question like this, like Na 1122 with a 1 plus in the corner, can you interpret what the heck I just wrote down on the board? Like, do you know what that means? Or is there a part of this jargon that you're like, I don't know what that's for? Let's just do a quick review. What does the 11 in the bottom corner refer to? Protons, which is what makes it sodium anyways, right? 11 protons is literally what makes it sodium. Well, this 22 right here is called a mass number. It tells you how heavy it is. And really all we care about is the nucleus. So what else is in the nucleus along with protons? Neutrons. Okay, well, a little bit of like basic arithmetic here. If there's 22 particles in the nucleus and 11 of them are protons, 22 minus 11 means there's 11 neutrons, because 11 and 11 adds up to the 22. Now there's a 1 plus charge though. If there's a charge in the corner, when I do electrons with protons, it can't be the same. Because if protons and electrons were the same, there'd be no charge whatsoever. If there's a +1 charge, there better be more protons. How many more protons? Well, 1 more proton. So, like, what's 1 less than 11, I guess? 10. There we go. If that's something that you're comfortable with and you can do, perfect. You're like my daughter, who's now kind of learning her letters. And she understands how they work. I got a game on the computer where she's got to learn, like, the different types of sounds letters can make. You know how, like, the letter A can make an A sound or an A sound? Right? It's kind of like that, right? Where you're learning, like, the intricacies of the elements. Today, we're now going to work on compounds. And compounds are like words where we're going to take Na, we're going to take Cl, and we're going to merge them together and make a compound. Now, you actually should have done a little bit of this stuff back in grade 9, so this may still be review for you. But like either way, give me your best attention here. Okay. So I'm going to go through my notes here now. There's actually 2 different types of compounds that we're going to learn about today. Maybe you know these words. One is called a molecular compound. Sometimes we use the word covalent. The other one's called an ionic compound. And I'm going to start off with the ionic ones because ionic compounds are made from ions. Like that's literally where the word comes from. Right? So let's do a quick review though. What makes something an ion? Ions have a charge. Yeah, ions have a charge, right? You know that example I just did there of sodium? Let me do a different one. Let's pick calcium. Calcium, I believe, is number 20. Yep, got it right. Calcium's number 20. Why don't I put a 39 up here? I don't really care about that. Let's say I don't put a charge in the corner here. That's an atom. And atoms have no reason to stick to other atoms because they're all neutral. Right? Neutral stuff doesn't stick together. But if it has a charge, like say a +2 charge, well then this positive thing may want to stick to like say iodide that's negative. There's a reason for them to stick together. You guys know that like positives and negatives, they attract each other, right? So that's kind of the idea, is that ionic compounds are made from positives and negatives between anions, which are negative, and cations, which are positive. And they are literally like they are attracted to each other. They stick together. That's ionic compounds. Okay. We're also going to talk about molecular compounds as well. And these also bond together, but there's a bit of a difference, is that they are both actually nonmetals. These are both going to be anions. And they kind of work a little bit different. So, but I'll get to that in my slides going forward. So let's do that review of ionic compounds. This is a great example of a diagram. This is a Bohr energy level diagram. That comes up on your assignment, I think. I ask you something about a Bohr energy level diagram. Quick review, because I think it's worth the time to do the review. Before Rutherford, they thought that matter looked something like this. They thought that there was like a positively charged like middle, and there were little bitty bits of electrons in the middle of it. This was Thomson. Remember what we called this model? Plum pudding, yeah. It was not bad, but it wasn't right. Because Rutherford discovered there was a nucleus, like a core, right in the middle. But Rutherford's idea was that this core in the middle, if I were to kind of draw it on a new slide here, that core in the middle, that there were electrons, and the electrons went around in circles. That they always went around in circles. And he knew that was wrong. Like, as soon as he made his hypothesis, he knew it couldn't be right. Bohr had almost the exact same idea, but Bohr suggested the electrons didn't actually go around in circles. They just went wherever the heck they wanted. But they would jump from like one level to another, and you'd never find an electron right here. Physically impossible. Oh. And so this is what we still use sometimes to represent electrons, these Bohr energy levels. Right? The classic example here is sodium and chlorine. Sodium as an atom is supposed to have 11 protons, 11 electrons, and chlorine as an atom has 17 and 17. But let's look at the energy levels. We call those valence electrons. Remember valence electrons? Those are the outside-most electrons. Basically, the idea is we either want it to be full or empty. Nowhere in between. It's either got to have a full energy level or an empty energy level or not. Well, look at sodium right here. Look at that outside-most ring of where electrons could inhabit. How many is out there? One. There's one valence electron. It's like he's got a little bit extra left over. I gave this analogy in class the other day. The idea of you want to go buy some stuff at the cafeteria, and they give you change. You buy something worth $5.75, you spend $6, and they give you back a quarter. So you have a little bit of excess left over. That's this valence electron here. It's just kind of uselessly floating out there. It's not in circles, though, by the way. We know they don't go in circles. But look at chlorine. Chlorine's got 1, 2, 3, 4, 5, 6, 7 valence electrons. How many do you normally want? Yeah, 8. We call it the octet rule. And so there's room for this electron right here. He needs one more. This is the guy that wants to go buy something at the cafeteria for $5.75, and he only has $5.50. So what do? You go around the room bumming your friends. Hey, you got a quarter? Hey, you got a quarter? Until eventually you come across a sodium who has an extra quarter and says, hey, I'll take that. Right? And that's literally what this little diagram right here shows. And what ends up happening is no longer is sodium and chlorine an atom, but now sodium is a positively charged ion. Chlorine is a negatively charged ion because they gained and lost electrons. And what do positives and negatives do? Attract. And now you have a bond. Does that make sense? That's how compounds form. So that's an ionic compound. Here's kind of a picture of the after scenario. Look at this outermost ring for sodium. How many electrons are in the outermost ring now? None, because it got rid of it, right? And now it's got a positive charge. Chlorine is now full. 1, 2, 3, 4, 5, 6, 7, 8. It's now got that negative charge, and they stick together. So we call that ionic because literally it involves ions. Okay. And sometimes what I'm going to do is I'll use these manipulatives I've made over here on the side wall. So I may be walking back and forth a bit today, but hopefully you guys can kind of visualize this. If you have somebody who is a +1, 1 positive, and someone who is a negative, see how they kind of fit together? I'm going to use these as we go through the class, these manipulatives, to kind of describe the idea about how the charges will fit with each other. Okay. So here's how we name these things. We always name the cation first. What are cations again? Positives, and they're also like the metals. Okay? So your metal always goes first. Whatever has the positive charge, we name first. And then the negative goes second. So whatever is positive is first, the negative goes second, and that's how we name it. For example, AgCl. What is Ag? Well, it's silver. What is Cl? It's chlorine. But here's how we change it, though. The second word, we don't call it silver and chlorine. We always change the ending to IDE-ide. It sounds better. So it'll be silver chloride, potassium oxide, and aluminum sulfide. Okay. So you always change the second word, the one that's the non-metal, to IDE. Now, some kids are going to ask, hey, Chris, that's cool, Ag and Cl. Why is there a 2 here? Or why is there a 2 and a 3 here? And that's what I want to use when I kind of use these manipulatives. So bear with me a second here while I bring these from this board over to here to the front. And maybe grab your periodic tables, because you're going to want them. So if anybody ever watches this video afterwards, I can't draw on the board anymore, so I'm kind of at the wall here. But hopefully you can still hear me if you ever watch this video. Just need to spread these out a bit. Let's talk about silver and chlorine. Okay. If you guys can find your periodic tables, can you find me the charge on silver and the charge on chlorine that's listed there? What are the charges for silver and chlorine? Okay. So I'm hearing -1 for chlorine, and silver is hopefully +1. Okay. Let's have to spread these out here. So again, I'm sorry for anybody who watches the video afterwards, because this part won't be as useful. So do come to class. But here's what I'm kind of looking to do. I just need a pen now. Noah, question? Oh, you have the answer. Yeah. So that's what we're going to write down here. So you said silver was +1? Yeah. And so here's how my manipulatives work here. If you have a +1 and a -1, can you guys see how they just fit together? How many of each did I need? Well, I needed one of these and one of these, which means you could even write it like this: silver 1, chlorine 1, because you needed 1 silver, you needed 1 chlorine. But like in math and science, like if we ever have one of something, we rarely if ever write the 1. We just kind of skip writing the 1. So that's where silver chloride came from. But let's try another one here. Let's try potassium, and oxide would be oxygen. Can someone find me potassium's charge and oxygen's charge on your periodic table? Okay, so potassium is +1. Thank you. Is everybody able to find those on your table as well? Okay. Again, this kind of goes back to my daughter being able to read. In order for me to teach you compounds, which are words, you need to be able to interpret your letters, which are elements. So hopefully you can find that. If not, well, we'll go over it at some point, right? Well, here's the difference now. We have a +1 now, but now we have a -2. Do they fit together? And hopefully the visual kind of makes sense. Well, no, because a +1 and a -2, they don't actually like merge properly. But you know what I can do? I can have a second +1 there. Now they fit. Well, now these guys right here are potassiums, and this guy right here is an oxygen. How many potassiums did I need? Yeah, that's why there's this little 2 down here in the corner, right? And how many oxygens did I need? 1, which is why I didn't bother writing the 1, because I'm lazy. Right? That makes sense? Let's try one more. Find me the charges for aluminum, and then sulfide was really a sulfur. Okay, just give me a sec to write these down here. I'll go above this time. Aluminum, someone says, is +3. -2 for sulfur? Okay. So again, I hope you guys can find those on your own. If not, I'll point them out, I guess, at some point. Okay. That's that whole building on the tower thing. Right? Hopefully, as I'm building on the tower, hopefully you got that down. So if aluminum is +3, here, I may as well erase all this stuff here. If aluminum is +3, and sulfur is -2, do they fit? No. We have too many positives. Okay, now here's what you can't do. I can't just do this, because I know that fits, but sulfur doesn't come in groups of -1. Sulfur always comes in groups of -2, so I can't use one of these. Okay, I got to be consistent. I can use another -2, though. Ah, crap, now I went too far the other way. Now there's too much negative. Okay, well, let's add another one of these. Ah, now there's too much positive. Ah, here we go. Can you guys visualize this? All right, and this explains those numbers in the corners. How many aluminums did we need? 2. How many sulfurs did we need? 3. Well, these are old. They don't stick very well anymore. Anybody ever seen that before? Like, you've covered this at some point in your lives? Is this kind of familiar? Okay. So this is what we need to practice and work on, is being able to name and write out the words for compounds. Okay. So, I mean, ionic compounds are really simple. Just name them. First word, second word, change the second word to "ide." So let's do some examples here. because you do need some practice, okay? Now, I don't give you a ton of examples in class, because really, I want you to do that in your labs or activities, in your assignments, right? That's where I'll find you some more practice to work on. But let's do a few examples here. Let's try to write out what sodium chloride would be. So, first thing we should do is find the symbols for sodium and chloride, which is chlorine. So, sodium is Na, and chlorine is Cl. We'll start with that. Now, that actually just happens to be the answer, but sometimes we need little numbers in the corners here. So what you may want to do is even just draw out my little manipulatives. Sodium was a +1 charge like this. Chlorine was a -1 charge like this. Do they fit together perfectly? Yeah, I just need one of each. I won't even bother writing the ones in the corner. We're good. Done. Call it a day. That's sodium chloride. But what if I use aluminum chloride? So it's Al and Cl. What is aluminum's charge? Okay, so I'm going to draw that here. Here's a +3. So here's a 1, a 2, a 3. So I'll draw like 3 little pluses there. And chlorine only comes in -1. That doesn't fit, does it? So I'm going to need more of them. I'm going to need a second one here. I'm going to need a third one here. And those things, they're always going to fall off. So this was +3, and these were all just -1s. What's the ratio? How many of each do I need? I needed 1 aluminum, and I needed 3 chlorines to make it fit. Kind of visualize that? Now, at first, you may even want to grab the manipulatives and kind of draw it out, but over time, you'll probably get better at just kind of feeling it out and seeing how it works. Okay. But if you need to, like literally draw it. Okay. I got another way I'll draw the next one here, because maybe drawing like these little like pronged things like on the board there, sometimes that's a little hard to draw. So I have another way I'll show you for the next one here. So first we got to figure out what calcium and nitrogen's charges are, because one is calcium and nitride is nitrogen. So what is calcium's charge? I think calcium's +2. You guys able to find that? So calcium is +2. And what's nitrogen? -3? Okay. Here's another way of drawing it out. I'm going to draw out a calcium in like a little bubble like this, and I'm just going to put 2 pluses. And my nitrogen, I'm going to draw a little bubble, and I'm going to put 3 negatives. Ah, crap, it's not even, right? I have more nitrogens. So I need to add more calciums. In order to do that, I need to draw another bubble, but it has to be the exact same. It has to have 2 more in it. Is it even? Okay, so let's draw another bubble of nitrogens. But again, nitrogen bubbles have to come in 3s. I can't just put it in a 1 all of a sudden. Ah, shoot, it still doesn't match up. But maybe you see where I'm going with this. Hey, if I draw another calcium one like this, now I think it matches. Because how much charge does each of them have now? 6, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Really, this is 3 times 2, and this is 2 times 3. And it equals 6. So we needed to have 3 calciums for every 2 nitrogens. So that's a skill I need you guys to work on. And maybe it's something you've done before. If not, that's fine. I will work on this with you. But this is this is why I need you guys to engage in things like my assignments and activities, because I've got questions in there to help you build and practice these skills. Does anybody have questions on that first little bit? Let's try the reverse of that. Over here, I've got a chemical formula. We just need to name it. And these ones are even easier. We don't even need to care about charges. We just need to literally write what we see. Like, so K, you just need to know what K stands for. It's potassium, yeah. Sometimes it's the same letter as the start of the word. Sometimes it's like Latin or French, but this one's potassium. And then Br is bromine, but we always change it to ide. So it's bromide. Bro. Or this one right here. Be is beryllium. And then oxygen becomes oxide. Perfect. Or Sr is strontium. And F is fluorine. So change it to fluoride. These ones are actually a lot easier because you don't even need to worry about those charges. You just like write what you see. Just change the second word to ide, and you're golden. Does that make sense? Okay. Now, that's probably the easier one of the two. It's called an ionic compound. It's where you have positives and negatives. But stuff bonds in more ways than that. Okay. When I have to teach you guys chemistry, we have to kind of like bite off a little at a time because there are weird and crazy exceptions to like all these rules. So, but like here's our first exception. We can actually have non-metals bind with each other, and they're called molecular compounds. And you guys are actually familiar with this through one, I'm sure you know, CO2. What do we call that? Carbon dioxide. But hang on a sec here. Carbon is a non-metal. Non-metal. And oxygen is also a non-metal. If you were to look at their charges, oxygen has a -2 charge, and carbon actually doesn't even list a charge on your table. But if it did list a charge, it might actually go with -4 based on its location in the table. And like that doesn't fit. Those don't go together. And so there are actually some weird exceptions where they bond differently. They're called molecular or covalent compounds. And what they do is they share their electrons. Rather than someone giving one away, they share. I want to use my analogy of the cafeteria again. Ionic compounds would be where someone has an extra quarter and somebody needs a quarter, and they say, here, you take it. I don't need it. That's an ionic compound. Covalent compounds would be like where you want to go buy something at the cafeteria for $5.75, and I have $2, and my friend has $3.75, and neither of us are really close. But if we pool our resources, we have enough. Say that one more time. Ionic compounds would be like, I have an extra quarter, and you're just shy. I'm just going to give you one of my extra ones. Right? So it's like the cost is $5.75, and I had $6. How much change did I get? 25 cents. My friend has $5.50. They need $5.75. I give them my quarter. Now we both win. That's an ionic compound. Covalent compounds are where someone brings $2, one brings $3.75, and you pool your resources and share them. And that's kind of how these non-metal bonds work. Okay? Now, the way you name them is very similar. You use the first element and the second element with the word "ide," but you have these weird prefixes in front. Remember how we called this carbon dioxide? Di is because there are, you're already ahead of me here, there's two of them. Yeah. Okay. So that's what I've got kind of talked about on this slide right here. And the key thing I need you guys to know is that they share their electrons. They collectively pool them to bond. And one of the cool things here is that it doesn't even have to just be two things. This is known as methanol. And it actually involves carbon, a whole bunch of hydrogen, and oxygen, and another hydrogen again. And they collectively pool their resources to kind of bond together. And so it's not that like one is positive and one is negative. It's like they share. Okay? Now, here's a chart that you may want to write down in your data booklets if you don't know these names already. They are like Latin prefixes for like the numbers. For example, like mono means 1, di means 2, tri, like as in tricycle, 3, tetra, like a Tetra Pak, means 4, pentagon for 5, hexagon for 6. Like you guys know some of these prefixes, right? Like octagon is 8. I might recommend, though, at some later time, maybe write these down on your periodic table in case you ever forget them. Because they're what we use to tell you how much of each thing there is in a covalent compound only. So only if both things are nonmetals do we use these words. Okay? I never want to see something like this, CaCl2. Don't call this, oops, I spelled that wrong already, calcium dichloride. And the reason why we wouldn't use that is that calcium was positive and chlorine was negative. That was ionic. So you don't even need to use a di or a tri. We only use dis and tris if like you have carbon and oxygen and they're both negatives. In that case, then use the things on this list. So make sure you're careful when you use dis and tris. You guys want to go back here? Okay. Don't forget, they're online, right? Print my notes off in advance. That really is a good learning strategy if you have them in front of you. I know some kids, they say, but I like to write notes I learn by writing notes. And I agree. I'm not saying you don't learn by writing notes, but why don't you have the notes in front of you first and then later write the notes down? That makes sense? I think it's more efficient that way. So I really want to recommend, come to class with notes printed. And if you want to write more stuff down later, go for it. But anyways, that's your call. We good? Okay, so let's try some examples. We already know the first one, right? CO2. Carbon dioxide. Yeah, by the way, if it ever starts with 1, we don't even bother with mono. Because really there was 1 carbon, that's actually mono, but we never start a word with mono something. So this is carbon, and then oxide, but because there were 2 oxygens, we call it dioxide. The only difference for this next one here is carbon oxide, but because there's 1 oxygen, we call it carbon monoxide. You guys heard of that before? Like, you gotta be careful around carbon monoxide because it'll actually suffocate you. So you might have a carbon monoxide detector in your house, especially if you have like a wood-burning fireplace. My camper has a carbon monoxide detector because I'm burning propane, and that could give off CO gas. Okay, now this one right here is a bit different because there is a 3 in front. So like, if there's a 3 in front, it better start with a tri. And if there is a 6 right here, it better be a hexa. Right? Like, I can even just start by knowing that. 3 means tri, 6 means hexa, like hexagon. So to tell you what they are. N is nitrogen, so I call it trinitrogen. And then hexa, it's hydrogen. Hydrogen changes to the word hydride. So sorry that's not as easy to read there, but that is trinitrogen hexahydride. N3H6. Oh, I have no idea. I mean, well, I don't know. I would have to look it up. If I wanted to know what it did and stuff, I would go find its MSDS sheet. Remember those? Like the sheets that tell you all their properties and stuff? And I'd read it and would be like, oh, this is explosive or this is corrosive. I have no idea. But like, I'd tell you that for almost all these compounds. Like, I know what some of them do off the top of my head, but like, I don't have, no one has them memorized. Well, let's try the opposite then. Let's say I give you some words and I want you to give me the formulas. This one's probably even easier. Silicon means, right, Si for silicon. Tetra, I do not put the 4 right next because the fluorine is what you have 4 of. It's kind of backwards, right? Like the silicon, there's 1 of. The tetra comes after the F. You guys see what I'm saying there? Some people, they do this. They go silicon, tetra, well, that means 4, fluoride. But what this meant now is that you have 4 silicons and 1 fluorine, and that's not what we wanted. Tetraphosphorus, okay, phosphorus is P, we want 4 of them. Deca is 10, so 10 oxygens. Ta-da. Nitrogen, di means 2. Oxygen is O, we need 1 of them. Do we write the 1 though? No, we always skip 1s, we're lazy. There we go. This is something that ideally you did in grade 9. So like, hopefully this is review, but like, that's back to my tower again there, right? The reason why I want to show you this again is I want to fill in some of those gaps. Maybe you didn't learn it at all very well last year and I'm starting from scratch. That's fine. I don't care. I don't care where our starting level is, but I do care that we get better and grow. Maybe you were really good at this last year. Hopefully I can help you get even better, right? Like, we are going to build on this. So last slide before a work slide here. There are some names that have hydrogen in them. These all have an H in them somewhere. And sometimes we give them a common name. The most common one, you guys are going to know, is water. Water is H2O. Technically, water should be dihydrogen monoxide. That's what its technical name is. But like, we don't ever call it that. And there are many compounds that have like a common name. So rather than calling them like carbon tetrahydride, dicarbon hexahydride, and however the heck we'd call this one here, sometimes we just give them common names. Okay. So I need you guys to memorize these or write them down. So while we're kind of writing things down on our periodic table, these are some of the most common ones we will use, but there are many more than this. So write down a couple of them. I mean, for sure you guys knew water, right? Hopefully. But this one's called methane, ethane, methanol, and ammonia. So write them down somewhere. Ethane. Ethane is a gas that you might find used in, like maybe as like a camping fuel. You might find that. It's slightly smaller than propane, and so it's lighter than propane, but it doesn't burn quite as well. Like, you ever gone camping and used like a propane stove, or like your barbecue in the backyard, right? Those big like white canisters, that's propane. Ethane would be like a substitute for it that's just a little bit lighter, but it doesn't quite burn as well. But it's a flammable gas, basically. Methane is actually the gas that we use to heat most furnaces. So like if your house has a natural gas line coming into your house, that probably is running methane. They actually put an additive into it to make it smell, just in case there's a methane leak. If anybody has a gas stove, like that your mom would cook supper on, right, one of those gas stoves, it probably runs on methane. Anyways. Okay, I'm going to stop the recording in a second here because I want to give you guys some practice time. I'm going to preach this learning cycle at you guys a ton because I believe in it. Not only do I believe in it, though, I've seen it be successful in my students. Okay, so I'm going to preach it to you until you guys get sick of me hearing it. I've now given you guys some knowledge. Hopefully buy-in's already here. Hopefully you guys are here purposefully because you want to learn. Hopefully. If not, I'll keep working on buy-in. I've now taught you something, maybe for the second time, maybe for the first time. But you guys need to apply it and try it. So here's what I want to do for the rest of class. I want to give you guys some time to apply your knowledge and try some practice questions. And then before you leave today, I want to give you some feedback. So here's what I'm going to do. I'm going to give you guys about 15 minutes or so to try these questions either by yourself in a group. And then later, I'm just going to quietly, I'm not even going to tell you guys, I'm going to quietly grab my board and I'm going to put the answers up. Okay? If you're not done yet, don't look. If you are done, look and see whether you're getting it right. If you're getting it right, fantastic. That's awesome. If you aren't, call me over and I will try to help you. Right? But I don't want to end the class with just me ending it there and saying, okay, I'm done, guys. I want you guys to now apply this and get some feedback before you leave for the day so you know how you're doing. Does that make sense? So I'll stop the video. I'll even put on a radio station. That's all I've got left. Try these, see how you're doing. And in about 15 minutes, I'll put up the answers. Sound good? Okay.